I'm Darcy Barron. I'm at the University of New Mexico. This is actually a picture of the site where I do most of my observations, which is in Chile in the Atacama Desert. I'll talk a little bit more about this in my talk. Oh, sorry, it's doing, okay. So, you think I'd be used to this by now. All right, so there's sort of three different topics that I'm going to cover, and I'll try to, again, questions throughout is great, and I'll sort of stop at each one and make sure we're all on the same page here. So I'll talk about the scientific motivation behind the measurements that we're doing, these precision measurements of the cosmic microwave background, how we do these measurements, which is, pretty interesting and very different from the rest of radio astronomy. And I'll talk about the upcoming instruments that we're building and the surveys that we're going to do. And one thing that my work lately has been really focused on assessing the impact of RFI. RFI has always been a problem, but at these remote sites, basically the only transmitter that can get close to you is satellites, and we're starting to be more worried about how crowded the sky is getting. So the motivation behind all of these measurements is the cosmic microwave background. We've been measuring this for I think coming up on 60 years now, ever since it was first discovered. And we're getting sort of better and better at measuring it more precisely. This is really interesting because it really is this snapshot of the early universe coming from a single instant in time. It's the earliest light we can see in the universe. And so in measuring that sort of surface, we can study the physics of the early universe from what's encoded in that image that we take. But lately, we're also using it as a backlight. The CMB has been so well studied and so well characterized that we understand what has happened to it on its way to us as matter in the later universe deflects it through gravitational lensing. And this is a more emerging technique of studying where everything is in the universe by seeing how it deflects this backlight from the CMB. We have measured the temperature of the CMB to exquisite precision using a series of satellites, the most recent being the Planck satellite. It measures this power spectrum of the CMB, which is power at different angular scales. And that's actually how we fit our models of the universe. You can fit to this curve as measured by the Planck satellite with a 6-parameter model, the lambda CDM model that tells us that we think that there's, it appears that there's dark energy and dark matter in our universe. That fits really great, as you can see from this line here. And this also agrees with most of our measurements of the later universe, structure, galaxies, and things like that. So what I have been measuring, and where the field is going recently, is measuring the polarization of the CMB. So not just temperature, but how it is polarized. And we actually have a really convenient way to describe this polarization. We split it into E-mode polarization patterns. So this is not the polarization of a single photon. This is the polarization pattern on the sky. And you can describe it in terms of this sort of curl-free mode and divergence-free mode, E-modes and B-modes, sort of named in parallel to this E-mode looks a bit like an electric field. The B-mode looks like a magnetic field, swirling around. And these are mathematically distinct. You can break these up into these two different things. Why is this convenient? E-mode polarization, the ones that look like the top two, come from scalar perturbations, which I mean the density fluctuations that you see by eye in the temperature map, the hot and cold spots. Those are just density fluctuations in that plasma. B-modes, these swirling patterns, would only arise if there were tensor perturbations, where tensor perturbations are the stretching and squeezing of space-time like what happens with gravitational waves as they pass through LIGO, and like gravitational waves would have stretched and squeezed the plasma at the moment that the CMB was formed. So this is how we sort of parameterize a lot of our measurements. Since we've measured these scalar perturbations really, really well, we measure them to extremely high significance, and we're still searching for any hint of these tensor perturbations or B-modes in the CMB. These B-modes, again, are what we study now. This is this signature of inflation in the early universe. Again, this gravitational waves stretching and squeezing space-time would have imprinted this pattern on the CMB and would tell us about the energy scale of inflation and what the very beginnings of the universe were like. But we've also studied this B-mode polarization through gravitational lensing, where now we have E-mode polarization, and it's been twisted into B-mode polarization because of the gravitational lensing of light as it deflects around structure. So you see this where you know that there shouldn't be any, and you can actually track that back to matter that deflected it on its way to you. We look at this again in terms of a power spectrum, so power on different angular scales. Again, here's the very bright E-modes up here. This is the blue line. This has been measured pretty well. We're still improving on it. Below down here are the B-mode predicted levels, where actually this green line here is an echo of the blue line of this partial twisting of E-modes into B-modes from structure in the universe through gravitational lensing. And this is what we've started to measure and use to study matter in the universe and its distribution. The red line here is what has not been measured yet. This is this signal from inflation that's much lower than any of these, and is also peaking on larger angular scales. So you need a bigger survey to get to the same, to be able to detect this. Maybe I'll stop here if there's any questions. I don't see anything in the chat, but feel free to raise hands or put something in the chat. All right, I know I'm zooming through the cosmology so we can get to the fun part, the instrument. Okay, but so here is where the field stands as of, I guess this is from last year, but this plot here is representing 15 years, over 15 years of measurements of the polarization of the CMB, where a lot of these plots, a lot of these points are upper limits placed by, a decade of experiments who were trying to detect this, but didn't quite get to the right sensitivity. We finally started making measurements in about 2015 of this red, this red line here of the gravitational lensing peak. And we're still searching for these inflationary B-modes. So I have the moon here to sort of anchor your sense for angular scales on this plot, because we're looking at fairly big angular scales here, the degree scale down to sort of arc minute. I can sort of focus in on these. So again, here, this sort of box here is showing these detections. These are measurements that have been made over the past I guess 7 years that are getting better. These look something like this. So this, for example, is POLARBEAR, my project for my PhD, where we detected gravitational lensing by really focusing on a very tiny patch of the sky. This is a 4x4 patch shown here. We measured 3 of them because we're in Chile, and so each patch sort of rises and sets, and then you move on to the next one throughout the day to keep making more measurements. So these three very small patches were just named by their position and right ascension. You can sort of see that they're spaced out so that we could jump from one to the next as they rise and set. But in focusing down on this very, very, very tiny patch of the sky, to sort of focus all your integration time, we spent 1 year integrating down on these tiny patches And we got this first detection of this very, very faint signal. You can sort of see this is the equivalent power spectrum in the bottom right. Very big error bars, but you know, some of them are small enough to say, you know, this, we definitely detected this. And other experiments did too. The other side of this that POLARBEAR and other experiments are still searching after, back to this power spectrum plot, is this sort of lower left corner here, which is the hard part. You know, we need, if you're looking at this plot, going to the left means you're looking at the largest angular scales, measuring fluctuations on, you know, the entire sky at the far limit, you know, big patches of the sky here. And you're also going down in sensitivity, and, you know, sensitivity is sort of this fixed quantity. The larger the area of the sky you measure, the less sensitivity you'll have, you know, across it. So you build better instruments to really dig down into this lower left corner here, where we have a lot of motivation, because this is where we think there might be some really interesting signals from the early universe. The sort of leading edge of these measurements is the BICEP-Keck program, which is actually a telescope that barely even looks like a telescope. You can see in this lower right here. It's a refracting telescope, purely refracting. The aperture is a half a meter. You can see compared to this cartoon of a guy here. So they really only have, you know, degree resolution on the sky, but that's all you need. And that's also, you know, better in some ways if you're going after a big signal, to focus on those big scales and really get as much sensitivity as possible. So it's, you know, a very different approach, but what has been leading to sort of these very deepest measurements. They're focusing on 1.5% of the sky, which still is not that big, but is much bigger than the 4x4 degree patches. And since they're at the South Pole, they're able to just, you know, stare at it all winter long and really integrate down. And so, you know, they're the ones who have set the best upper limits, but they still haven't found anything yet. There's a big challenge here. You may remember from a few years ago when BICEP-2 claimed to detect inflation, but it turns out that our galaxy is complicated. Maybe the astronomers could have warned us, but it's actually quite complicated and has quite coherent polarization in certain patches. This may look like a painting. This is actually measurements from the Planck satellite, measuring the, through measurements of emission from dust in the galaxy, you can get at the alignment of the magnetic field and its density. So dust grains align under the magnetic field if they're slightly, you know, asymmetric. You think of some slightly elongated grain that aligns, and then also causes this, you know, preferred polarized emission. So, you know, we know that the inner galaxy would be, you know, highly polarized and highly complicated. But you might think you could look away from the galaxy, say this upper left blue spot where the dust isn't as bright. But actually that sort of backfires. If you look at some very thin patch of dust, you're really only looking through maybe a couple of filaments of the galaxy, and it becomes very coherent. So everything is aligned in a very similar way, which is actually bad if you're trying to find polarization patterns. You know, it's better off if it all decoheres as you look through many, many layers of dust. So it's a challenge, but I think it's more making the measurement more challenging, which is fun for us. We get to build bigger, more complicated instruments. It's not a fundamental limitation in searching for this signal. And this is, you know, this is a technique that we've done before with other experiments in temperature. The CMB is not the only thing emitting microwave radiation. And it has a very unique spectral signature. The cosmic microwave background is just a black body. And so it has a peak of around 150 gigahertz, but we can measure on either side of that. This plot here, oh, okay, oh, yeah, sorry, I was remembering my plot. Yeah, so this was an example with the WMAP satellite, which measured the temperature very well. and subtracted off these other components here. This is what it looks like for polarization now. So the CMB temperature was brighter than the other components, but you still wanted to measure them off to make sure your measurement was good. This is what it looks like for polarization, where now the CMB signal is much fainter than the temperature, and these other sources in our galaxy are brighter. So the main two that we worry about are synchrotron, which is electrons accelerating and spewing off polarized light, and dust. Like I said, dust aligning under magnetic fields and then emitting radiation in a polarized way because of that alignment. So you have the CMB black body, which is this teal line, and so you're able to measure it across many different frequencies, and you know how you expect it to behave. And then we also have pretty straightforward different spectral characteristics of these other components, where we know that synchrotron will be dropping very rapidly with frequency, and dust is rising up. There's sort of a minimum between those two that unfortunately doesn't fall lower than the CMB signal. So you know that you need to measure across all of these frequency bands in order to subtract out these galactic components and get your CMB signal. These are all in gigahertz. If it wasn't, I guess it's on the x-axis here. So this is how we do our measurements. We're doing this, spread of a factor of 10 in bandwidth around the central CMB frequency. We can't get away with just measuring at 150 gigahertz. You measure from 30 to 300 basically to get at this signal. Okay, so I'll stop again, see if there's any questions so far. All right, and I think I'm doing pretty good on time. Okay, so that's what we're trying to measure and what's the cosmology behind this. And so now I'll talk a little bit about the measurement techniques that we're using. So for example, here, this is what one of these CMB telescopes looks like. Maybe looks a little like a radio telescope, but not exactly. So this telescope here is POLARBEAR. So this is a telescope that was designed for polarization measurements. So there's a couple of different features I can point out here. One of them is, because this is doing polarization measurements, the primary mirror is a monolithic piece of aluminum. This was just precision machined aluminum. This is not panels that you put together. Any gaps in this, there's some in the outer area, but the central area, you don't want gaps or segments because all of those edges would cause diffraction, to cause some extra polarized light to come off. And we're trying to avoid any extra sources of polarization here. So our mirror is just one big piece of aluminum. And it's hard to make a piece of aluminum very big. So we're limited to about 2.5 meter aperture here, which is good enough for the CMB measurements that we're doing. Actually, by coincidence, the resolution of this telescope in the microwave is the same as the resolution of your eye in the optical, a couple of arc minutes. Again, that's enough for the signals that we're going after. This is also, again, for polarization reasons, an off-axis design. So there's no, support structures or anything like that that could also scatter light and induce polarization on its way. So the secondary mirror is actually hidden in here. Everything is very hidden because there's a lot of shielding to block any stray light from coming in from the environment. So again, I guess as a reminder of how we're doing these measurements, you've probably seen this plot before from NASA of atmospheric opacity. We're actually measuring right here, which doesn't look, it looks pretty opaque in this NASA plot. And if you're sitting well, if you're sitting on like the East Coast, it's pretty opaque. Although some of us in the West here, we actually have pretty good transparency. But if you really want to measure this, 1 millimeter wavelength, which is blocked by atmospheric gases, including water and oxygen, there's really only 3 places to go. There's a few others that are suitable, but there's really the 3 best sites. So space is obvious, but space is hard. Space missions take a lot of planning and actually have some downsides for polarization measurements. So really, oh, let's see, is there ambient air inside POLARBEAR? Oh, I think I'll get back to that later. I'll talk more about POLARBEAR. That was just sort of the telescope. But so I guess to motivate where we are, and you can see POLARBEAR sitting on this bottom plot here. There's 2 sites in the world that are have a dry enough atmosphere to do these measurements, because water really is the primary absorber. So the South Pole is one of them, because the South Pole is actually quite high altitude and actually a very dry desert, just because of anything that could precipitate is sort of frozen. And the Atacama Desert, which is also extremely high altitude, and has this double rain shadow from the 2 mountain ranges, leading to exceptionally dry atmospheric conditions. There it goes. Okay, so this is a more detailed view of now atmospheric transmission in Chile at the POLARBEAR site, where we have, around the CMB spectral peak, the transmission is regularly, close to 100%. Where anywhere else in the world, this would be down, 50% or lower. And this is because, we quantify this with PWV, which is precipitable water vapor. So that's how much water is in the column above you in the entire atmosphere. At our site in Chile, on a good day, this is 0.5 millimeter of water in the entire column above us. On a typical day, it's more like 2 millimeters, which is still very good. I think in New Mexico, where I am, the driest days are maybe 10 millimeters. In California, I think even the very, very dry days are still many times that. And that's partly because the scale height of water in the atmosphere is quite low. Water falls off very rapidly. Oxygen, we also know, falls off with altitude. Sitting at Albuquerque, I still have most of the oxygen. If I go all the way up to Mount Everest, I'm down to 1/3 of the oxygen is left in the air. I have to go all the way up to 30,000 feet to lose most of my oxygen. All I have to do is go to the elevation of Albuquerque to be down to 1/3 of the water in the atmosphere. Water is much heavier, so at 5,000 feet, you're down to 1/3 of the water. If you go up to 17,000 feet where POLARBEAR is, really there's just no water left. It's all below you. Okay, so let's see. Someone's asking about axes for polarization measurement. I think I have that in a backup slide. I think that will be obvious when I show the antenna too. The other thing was asking about SOFIA. So SOFIA, the other thing that I think I'm about to motivate, you really need years of integration time. So SOFIA is the 747 that has a big enough mirror, but SOFIA observations are hours, where really you need at least a month of measurements. And I don't think SOFIA can be refueled that many times. So that's why we do these measurements from the ground. And I think this detector will explain a little bit about why we need so much time. So we're in the microwave, but actually we get to skip a lot of the microwave and RF engineering because our detectors are not coherent detectors. We don't couple to the electromagnetic radiation with an oscillator or anything like that. We measure it through absorbing the power onto a bolometer. So bolometer is sort of a general name for this type of detector that absorbs incident power and measures the rise in temperature. There's also some weak thermal link down to a thermal reservoir so that it doesn't just constantly heat up. You measure power and through measuring the temperature rise. And why do we do this? Actually, so bolometer noise is limited by phonon noise. So phonons are the vibration, the unit of energy for vibration for things with temperature. If you're going to measure power and temperature rise, you're limited in some ways by that vibrational noise, but you can get rid of it by getting very cold. At absolute zero, nothing is moving anymore. There would be 0 phonons fluctuating around. All we have to do is get to 0.3 Kelvin, which is actually pretty easy. There's been a lot of advances there. You could just buy, if you had enough money, you could buy something that would get you to 0.3 Kelvin as a, random individual. Quantum computing people do this now. So that may sound very cold, but it's actually pretty achievable. If you have a bolometer and you cool it to 0.3 Kelvin, then your detector noise is only limited by the atmosphere, the photon noise coming from the atmosphere, which also has, random fluctuations in nature. But if you're at a site like Chile or the South Pole, it's actually quite low. So in this, very specific frequency range for microwaves, it's actually a bit like, optical detectors where you're only limited by photon noise. It's not like radio receivers where you've got some system temperature. We can really remove the noise impact of our instrument by designing these bolometers and doing it right. So, that's good and bad. We can build the best detector that you could possibly make that has a noise that's only limited by what we're trying to measure and measure through the atmosphere. But if you want to do a better measurement to get better sensitivity, you just have to make more detectors. And as we're measuring the CMB to more and more precision, we need more and more detectors and more integration time. The other reason why this works so well, and this is why the standard in the past, I guess, 2 decades has been to do it like this, we can make very, very good thermometers by using superconducting materials. So this is the superconducting transition of an aluminum titanium bilayer, which is a way to sort of adjust the superconducting transition to exactly where you want it to be. And you can see as this metal goes superconducting, it's not an instant transition. There's a very, very steep slope here where the resistance is dropping really rapidly with temperature. So you can use this like a thermistor and just say, within this range here, I have an extremely rapid, derivative of my resistance. And so I can measure temperature extremely accurately. This also works out extremely well because you guys all have your ham radio license, so I think you'll understand a bit about the circuit diagram here. So what we do, we have, what is really just a resistor, this resistor of the bolometer. It's dropping its resistance extremely rapidly with temperature. And so we put a voltage bias across it. You've got to turn on your detector with a voltage bias, and that sets up some electrical power, which is V squared over R. Now you have some optical power coming in, adding power, heating it up. But these two terms balance each other out because the resistance drops with temperature and goes up with incident power. So if optical power comes in, resistance goes up, that drops the electrical power. So if you do this right and your transition is very steep, which means you have very good loop gain, this total power is constant. These two feedback against each other. We call it electrothermal feedback. to have a constant power on your detector, which is what you want if you're trying to, stably measure a signal on the sky and record it. If you had this, the other way, if the resistance was increasing with temperature, like you would have with a semiconductor bolometer, you could also do this. It's not quite as good. You could current bias it, and then the same thing would happen. But it's all about the steepness of the curve, which really keeps the feedback very, very strong. So this is what this actually looks like. This is a scanning electron micrograph of one of these bolometers, where this resistor, this thermistor, is this tiny little piece of metal here. And you can see that this is this island that's extremely thermally isolated. You absorb power on this island here, and then it, sort of slowly dumps it off to the wafer here. This may look complicated, but actually, this is using a lot of the same techniques that industry uses to make, the processors in your computer and all sorts of things. So we can do this actually very well. Actually, I guess I'll get back to that. It's very convenient that we can just produce, thousands and thousands of these on a silicon wafer. Let's see, I think I'll skip this, this just to, I guess, if we want to ask it in the questions later. Actually, to read out many detectors, you need to be careful with wiring, and we actually use techniques just like AM radio to modulate, set up our information on different frequency channels and read it out, but I'll skip this. So this is what a focal plane looks like. This is what the camera looks like for these instruments. You have, let's see, I think okay, here's the one. Okay, and this maybe answers a little bit about the question about defining polarization angles. You can take a silicon wafer. This is a 6-inch silicon wafer, and you have someone in the lithography lab, nanofabrication facility, who sets this up and can precisely machine many copies of these. Again, using the same techniques as Intel uses to make processors. There's a little bit of special stuff with the superconducting metals, but it's still something that there's many facilities who can do this. This pink is a zoom in on, okay, so now what does a pixel actually look like? I showed you the zoom in of the bolometer. Here's actually these bolometers on the side here. These are coupled to our antenna, which looks a bit wild. This is a sinuous antenna. So this is what an antenna looks like. I'm sure you're all familiar with log periodic antennas. You're trying to have different length scales to couple to the different frequencies of light that you care about. This is what that antenna looks like if you want to preserve polarization information. So there's 4 different detectors here because you're coupling to the perpendicular, this way and this way of light. So there's actually 4 arms. 2 of the arms are sensitive, to the vertical polarization. 2 of the arms are sensitive to the horizontal. It's not perfect. There's actually a little bit of a wobble as you go out to different frequencies in that exact polarization angle. It sort of goes like this, but it works well enough. And we have to do this. We have to be broadband because of, getting back at this sensitivity thing. We need to collect as many photons as possible. So our bandwidths are huge. And these are, defined on chip. So we're not a coherent receiver. We can't scan across frequencies. We design our antenna to just accept all light in a broad frequency range. So this plot here is showing, this is a measurement of, which frequency bands the 2 different sections, sort of the 2 halves of the arms are sensitive to. We break this out into 2 different bins with a, sort of a pretty broad bandwidth, 70 to 100 gigahertz and about 110 to 150 gigahertz. We're designing those to match the atmospheric transmission windows. Here's just another, so what are all these fly eyes on the wafer? We just have little lenslets to couple to this antenna. You have to anti-reflection coat your lenslet to sort of, make sure there's not stray reflections. That's actually pretty straightforward, 2 different layers, does a good enough job. And you put these all together. These techniques are, actually really straightforward to scale up. I think these pictures here are from sort of 15, 20 years of CMB experiments. Bicep 1 was the project that I worked on as an early grad student on some of the data that it had already taken. This is a sort of, hand assembled thing where you had some, poor grad student hand assemble each of these detectors. As you jump to, for example, Apex SZ, and you start to fabricate things on silicon wafers, it becomes much easier to make things uniform, which is great for precision measurements, and to make more of them. And so from Apex to POLARBEAR 1 to POLARBEAR 2, part of this is going to bigger wafer sizes, going to entire wafers, and trying to keep up, sort of like the uniformity of this process. It looks all very fancy and uniform, and the mask that you put in that tells the machines what to make is very precise. But uniformity across these wafers is always really hard. You may have heard Intel, makes these on, I think maybe 12 or 18-inch wafers now as it's making processors. And the reason your processor is an i3, i5, i7, i9 is actually, what did the best in this process. They pick it out and decide what has the most working parts. We want all the parts to work because we can't just say, oh, we'll sell this as a lower grade processor. No, we need every single pixel to work as equally well as the other one. So while we're using those processes, I think we realize that we actually have it a lot tougher than what they can do. We're trying to keep this whole thing uniform and alive, but it does work very well. So this is, again, POLARBEAR 2 has 8,000 of these detectors across 2,000 pixels to observe the CMB at 2 different frequency bands. Okay, I'll pause there again. I saw, let's see, I don't think there were questions, any more questions I didn't cover in the chat yet, but I'll sort of pause here as we go to what's next. I see someone just joined as well. All right. So this is what we've built right now, and I guess as you can see, because these are pictures of as built, as scanning the sky right now, that whole thing is put under vacuum so that it can get down to 0.3 Kelvin. I think that's the part that I didn't quite cover. Sorry, I'm going the wrong way. So this whole thing is held at 0.3 Kelvin under vacuum and put on the telescope. It's hard to point out exactly where it is on the telescope because everything's so well shielded, but this is the part that faces the sky and scans, makes the images. So now I'll talk about what's coming next. We've gotten really good at making these detectors and making these measurements, and now we're getting even more ambitious in our goals here. I showed you a little bit about the current state of measurements, where we have measurements of the lensing B modes, which is green on this plot, and this search for the inflationary gravitational wave B modes here. These were done by, there's been more than a dozen experiments doing this over the past 10 years, and there's been 4 who have been successful in making measurements. But I think this slide sort of describes where we're at here. We've all sort of done the not easy parts, but the straightforward, let's measure a small patch of sky, see that we can detect the signal. Bicep has done a lot of work searching for the more faint signals. But given what we know about how complex our galaxy is as a foreground, with dust and synchrotron obscuring things, and given what we know about how much of the sky we need to measure to really do this, again, these sort of demonstrations on small patches to detect it are not the same thing as characterizing it over the entire sky. So, I like the way that they put this in this slide from John Carlstrom at the University of Chicago. We've really hit rock here. We've really gotten to the hard part. And so as a field, we've decided you can't make any more progress with, small groups and single telescopes trying to make these measurements. It would take another 50 years. We really have to sort of all band together to do this and measure it over the entire sky. There's all these, funding agency mechanisms to try to understand what's possible. This is an example. They had a concept definition team that defined an instrument that could make these measurements. And you end up realizing that you need something like 14 small refracting telescopes and 3 6-meter class telescopes. And detector counts that are, more than an order of magnitude more than anyone has deployed to date. This is also describing all of the different frequency bands that you need to cover. So, again, 20 to 270 gigahertz needs to be covered to recover the CMB from the astrophysical signals. And you need small cameras to get these large angular scales successfully, and slightly large telescopes, 6-meter, to measure the gravitational lensing signal and to, provide information at these smaller angular scales. Oh, yeah, and someone's asking about the dynamic range of the detector. That's a good point. These detectors have a very small dynamic range, and that's part of why you have to go to such a good site where the weather is just perfectly stable, because there's not a big range that you can work in. Here's sort of a slide showing the scale of what we have realized that we need to build. This is sort of showing similar to those the POLARBEAR 2 wafer modules with the black lenslets that you could see. This is how many of those we need for CMBS4. This is something like 9 king-size beds of detectors that need to be held to, fractions of a Kelvin. It's a pretty big effort. But we have gotten sort of the nod from the Astro 2020 survey that said, what are the priorities in astronomy? That said, this is going to cost about 660 million, which is a lot of money, but compared to James Webb and VLA and ALMA and stuff like that, this is actually pretty small. They say, this needs to go ahead. This is really exciting. So that's really good that this should all be going ahead. Our survey, again, the real point of this is now let's scale this up to the entire sky. And this is sort of, us comparing to, since we have telescopes in Chile, you sort of see this southern part of the sky that has good overlaps with LSST, which is now the Rubin Observatory, and all of these other sort of surveys of the sky in the optical and other wavelengths. So to show, I get sort of this plot shows, what we've been up to, and I guess a cartoon of where we're going. Again, this sensitivity, this is trying to show this background limited sensitivity means that to get to the sensitivity that you want, this is a plot of the BICEP program sensitivity at various frequencies across over a decade of observations. And so you just keep scanning and scanning the sky. These all have this sort of square root form where it's a log scale. So that's why it sort of seems to flatten out. And you make jumps in sensitivity by, adding another camera, adding more detectors to the sky. So this is this trend that we're trying to continue on with CMBS4, going off of what we have accomplished. And now let's just continue on, more detectors, jump down to this nanokelvin level of sensitivity. But one challenge, aside from all of the engineering challenges, is coming from RFI. We built these really precise, sensitive instruments. And this is a nice example of, I guess, sort of just how sensitive we are. So this is coming from SPT3G, which is one of the current CMB surveys at the South Pole. That is one of the groups that's working on CMBS4. This is their the time streams off of their detectors, off of their bolometers. And this is them detecting GRACE FO, which is a NASA Earth survey satellite that has a K-band antenna. And so you may wonder, what are we doing detecting a K-band antenna? This is the 6th order harmonic coming off of their transmitter that we've measured. And you see this to high significance, and this messes up your measurement. You know, you've got to cut all this data. This is not too bad, at least it's not saturating it and exceeding the dynamic range, which is what was mentioned in the chat. But still, we can see very, very faint things. This is becoming a concern. We're about to get so much more sensitive and survey so much more of the sky at the same time that the sky is getting a lot more crowded. This, at least there's, you've seen this, I'm sure too, there's allocations in the radio spectrum. This is very highly regulated. But what's shown on this slide is actually perfectly allowed. These are all within the regulation limits for harmonic emission, because they sort of weren't thinking that you could have something so sensitive. And maybe they didn't realize you could have 6th order harmonics be so strong either. But there is a whole space to try to work with here. But for CMB measurements, we're not really well protected by this. This is an example here of, this is an atmospheric transmission in gray, which is sort of setting where we can measure and how transparent the atmosphere is. In blue are our bands. Or again, like I showed you with that antenna, you really define this with a filter before your detector. So your antenna absorbs light, you filter it into these broad bins with these on-chip filters, and then everything that you see is combined into one signal. For example, this 200 to 250 gigahertz. You can't distinguish between frequencies in here. We've got these huge broad bands, broad fractional bandwidths on the sky to boost our sensitivity, but that means we're crossing tons of unprotected spectrum. These green bands here are the radio astronomy primary allocations, where radio astronomy takes precedence. That doesn't mean no one can transmit, but it is the most tightly regulated space. And we're really observing across very broad sections of unprotected space here, especially at the lowest frequencies where lots of communication stuff is happening. We're also just vulnerable to RFI. We can't fully enclose our telescopes because they are observing the sky. I showed just a bunch of examples of current instruments and what they look like. You can see they're all very highly shielded, but they all have some aperture that opens up to the sky, and radio waves can couple in. And if we want to keep our sensitivity very high, and we can't put like a mesh filter across that, that'd ruin our science signal too. So actually a lot of these have a very similar scale of aperture of about 0.5 meter, which is actually unfortunately good at coupling in certain like hundreds of megahertz wavelengths. But that's why we're at the most remote sites in the world. So that's not something we have to worry about for radios and Wi-Fi and stuff like that. But we are very worried about satellites. These satellites are using these gigahertz frequency bands, K-band, Ka band, to communicate. We're at the most remote sites on Earth. I have seen a plane fly over once in my, multiple years of being in Chile. That's how remote we are. But no one can hide from satellites, not even the South Pole. This is an example from the Vera Rubin Observatory, which is also very worried about this, of sort of what the sky looks like now for satellites and what it might look like with a full build out of Starlink and OneWeb and Kuiper, where all of a sudden there's sort of no clear paths to look. And if these are all maybe not transmitting in your band, but have harmonics that aren't well controlled or side lobes and things like that, things that we all understand very well as radio engineers, that are hard to eliminate, harmonics and side lobes and stuff like that. This could be very ugly. So it's something that we're working on. But I can take questions about that too. We're not very well protected, and we're getting more worried. So I'll end. So this slide here, where to read more about CMBS4, this big project. We're now a line item in the congressional budget too. As you're reading through your congressional budget, you can see how many $1 million they give us each year or don't give us each year. Recently, the CERN Courier had a really nice cover story on us. And I'm starting to work on this proceedings for the SPIE Astronomical Telescopes and Instrumentation Conference on our assessment of these impacts of RFI on our survey and how we can try to mitigate it in various ways. So, all right, on there, and hopefully we have time for questions. Thank you.
Thank you very much, Dr. Barron. I see there's a couple of remarks in the chat window, and also anybody has any other questions. I know we're all concerned about the impact of such satellite constellations as Starlink. They are really serious threats to radio astronomy, and we really have to do something about this kind of thing. So anybody who wants to ask Dr. Barron questions about what she's presenting to us, please go ahead.
Hello.
Hi.
Hi. You're looking at B-mode. Right now, you're looking at the effect of gravitational lensing, and yet you did specify that B-mode would be the result of magnetic fields. So you haven't actually detected B-mode signals from magnetic fields, have you?
Oh, yeah. So there's two things about the B-modes from the early universe are not from magnetic fields. It's just that the sort of the pattern is reminiscent of a magnetic field that has no divergence. The other thing about magnetic fields that we do detect is magnetic fields aligning dust in the galaxy, which some people care a lot about what the galactic magnetic field looks like. To us, it's something we need to understand well enough to get rid of.
Thank you.
I see, yeah, Marcus's good comment in the chat about, yeah, a lot of these requirements they're not really designed to protect radio astronomy, and a lot of them assume that you would never have a direct coupling, that satellites passing overhead are so rare that you would never look right at one. That one example, sure, is one example, but I think we're worried about is, as they proliferate by a factor of 1,000, how many, it'll be a lot easier to accidentally look right at one, coupled to its side lobes or its harmonics and things like that. So, yeah.
Yes, what about the impact of 40,000 satellites floating around the Earth, every possible orientation and location you can possibly imagine? It would really be overwhelming, I think.
Yeah, at least we're not the only ones concerned about this. There's even concerns about having that much debris in space and satellites in space and collisions and deorbiting. So I think there's a lot of people highly motivated to regulate this more tightly, not just for CMB measurements. We're sort of the long end of the, the tail end concern here.
Okay, thank you very much.